All right, we're going to look at electricity and magnetism, specifically electrodynamics, which is the study of motors and generators. Starting with basically where we use motors and generators. So AC generators are like the ones that are used at Eskom, and they're the ones that generate power for us from Eskom, okay? So electrical power plants, and that's whether it's coal-powered, nuclear powered, wind powered is also an AC generator, or hydroelectric. It doesn't matter. All of those are all AC generators. Solar panels are the photoelectric effect, so that's slightly different. Also, in our cars, we use a generator to recharge the battery, and that's actually quite important for us. Okay, it's part of the alternator. DC generators are used in bicycle dynamos. Now, you've probably seen a cyclist who has a light on the top front of their bike, which flickers. That's a DC generator, okay? It's a dynamo that creates electric current by the movement of the wheels. We also get them in battery chargers, so don't stress too much about that one. Motors, pretty much most household appliances have motors, so things like your hairdryer, a fan, if you have a convection oven, anything like that, even the thing that turns the plate on your in your microwave, that's a motor, okay? And then electrical cars, either way, they have an electrical motor in them, okay? So let's go and look at how a generator is used. So we need to remember that a generator works on the use of Faraday's law of electromagnetic induction, which says to us the magnitude, so the size of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage. So in other words, how fast we can turn a coil or a wire, move a wire in a magnetic field or a magnetic field over a wire, the faster, the greater the current is that we will induce, that we will make flow through the wires, okay? Now, last year you looked at this equation where EMF is equal to the number of turns times the change in magnetic flux and delta divided by delta T. The nice thing is this is not examinable, okay? So they're not going to ask you questions about this equation, which actually is really nice for us. So we don't need to stress too much about it. It's just to remind you about the factors that are important in terms of when we create an electric current. Now, to find the direction of the induced current, your textbooks use a slightly different rule, where I like to use this one. So if you look at the diagram, make sure you have your right hand, your thumb, so the top of your thumb always points in the direction that the wire is being moved in. All right, so in a generator, we're moving the wire, and your magnetic field, your fingers point in the direction of the magnetic field. Basically, your fingers must always point towards the South Pole. That's the easiest way to remember it, because magnetic fields always go from north to south, okay? And then the direction that your palm is pointing in. So you'll have it on with the wire, the direction your palm's pointing in gives you the direction that the current is moving in inside that piece of wire, okay? So when we look at an AC generator has a whole bunch of parts. They have a coil of wire, so placed inside the magnetic field. We'll do a diagram in a second. There are slip rings, please. This connection is incredibly important because basically it's just the slip ring compared to what we use in a commutator, compared to what we make in a DC generator that differentiates the type of current we're going to get. Carbon brushes are then in contact with the slip rings in order to maintain contact with the circuit so that the current that's created in the cell or in the wire can be transmitted to the rest of the external circuit. So if we look at our diagram, that should be poles. This is your slip ring, okay? So it's two rings that are connected to the coil, and as a result, the coil is free to move. Now, you will physically move the coil, okay? Don't worry about that. We'll deal with that in a second. Very important as well, an electric motor converts mechanical energy into electrical energy. So generator. So generator is mechanical energy to electrical energy. Very, 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 very important. We're now going to go through the operation of an AC generator. And over here, I have a little blue thing. It says a generator. There is a video that I've uploaded into Teams, which says how an AC generator works. Please, you need to go watch that because that'll help this make a little bit more sense. Okay, so when we have our generator, okay, we are moving this generator clockwise, so it's going to go up and then it's going to go down. So this wire here is moving up through the circuit. So what happens is the current is now going to go, and the magnetic field always north to south. So the current goes from A to B to C to D and then comes out. So if you look at this, I just want to change color here for you. A is connected to brush A1. D is connected to this part. Okay, so now my current in the external circuit is going to come out that way and go in there. Okay, so in the wire, it goes from A to B to C to D, and then it goes from 2 to 1. Okay, at this point, at this motion, it's now maximum magnetic flux, maximum current. If we now look at it turned once, when it gets to this position, there's no current. Okay, this is because the wire is actually moving for a brief moment parallel to the magnetic field. So it continues turning and it's going to keep turning because we're turning it. Okay, now we have no current, so side A and B, A, B, C, D move parallel to, it's very small, but it's enough for there to be no current. Then it turns over. What I now need you to see here is this. A, all right, is still connected to number 1. D, is still connected to 2. The difference here is, and I need you to fix this for me, please. The current still goes in this direction around the wire, okay? But now the current is going to come out of 1 and into 2. Okay, so out of 1 and into 2. So this is the wrong way around. So the current has changed direction in the external circuit as well. Before the current was going A, B, C, D. Now it's going D, C, B, A. It's changed direction. AC stands for alternating current. So the current has changed direction. It's alternated its direction. And it's gone from a minimum. So this is 0 current. This is now a maximum current, but it's a maximum current in the opposite direction. Once again, it gets back to the parallel section. So now it's reached the top. 0 magnetic flux. It's moving parallel. Okay. If we now draw the graph that comes from this, and this is for the induced current, please don't worry about those. Those should be time. Okay, you're not going to work with them as angles. So we have time. I'm not putting a value on here because I don't know what it is. But when it's flat, I get a maximum. When it's vertical, I get a minimum. Changes direction, going back to a maximum, back to a minimum, back to a maximum. Now this is the current, the graph we would get for a current, but it would be the same graph if this was potential difference. Okay, it would be exactly the same shape. The values would be different, but it's exactly the same shape. And the current and the potential difference have to go in the same direction at the same time. And if we have 0 current, we have 0 potential. Okay, with the DC generator, now the DC generator produces direct current in the external circuit. The slip rings are replaced by a commutator. Okay, very important. A commutator is a metal ring that splits into 2 halves, and there's a gap between the 2 halves. That gap is very important. Inside the coil, the current changes direction the whole time. I'll show you in a second. However, externally, outside the coil, it always looks like it's the same. So that's the point. So if we look here, and this is very important. Again, if we look at this A is connected to W over here, and B is connected to Z. Okay? So that's important. We move in that direction. We start moving, all right? The magnetic field, which isn't drawn here for you, but you can put it in, is going in that direction, so north to south. When it turns, we get the Y, so the direction of the current in the coil is from Z to Y to X to W, and then it goes from A, because it's coming out of W, through the circuit to B. Then it continues turning, nothing changes, the current's going to go from a maximum, now it's getting smaller and smaller and smaller. Then it gets to this position. Over here, there's no longer contact between the coil and the external circuit. That's what that little gap's for. But there's no current anyway, so that's not the problem. Now you need to pay attention to what happens. So there's no current. Now once it turns, at this point, W is now connected to B. It's no longer connected to A. Z is connected to A instead. Okay? So the current is going that way around the circuit. So instead of going Z, Y, X, W, it's now going W, X, Y, Z. So in other words, it's changed direction inside the coil, but the external circuit still sees that it's going from A to B. So outside the coil, the light bulb thinks that the current just keeps going in the same direction every single time. And that means it's getting a direct current. So make note. The current in the external circuit of a DC generator never changes direction. But it does change in size. Okay, because of the way it's created. If we look at the graph, again, let's just fix this, okay, because I took these from your textbook. This will be time, okay? This will not be given to you as angles. Minimum, because it's vertical. Maximum, because it's horizontal, maximum. Minimum, because it's vertical. Maximum, because it's horizontal. But the induced current is now always above the line, okay? If this was a potential difference graph, it would be exactly the same shape. There would be no difference in that shape. Okay, so that gets us to the end of part 1.